Our next speaker is Alexander Braverman, who will talk about an introduction to symplectic duality and Coulomb branches of 3D quantum field theories. Please, Sasha.
Okay, thank you very much. So first of all, I would like to apologize that I'm not giving this talk in person. So I was really planning to be there for this week, but for some unforeseen circumstances because of which I couldn't come. And I decided to slightly change the structure of my talk compared to what I originally announced. So, well, the idea was this is, as Anton told me, this is primarily supposed to be aimed at, students and young people. So I wanted to give some kind of survey, but I wanted to maybe slightly shift the emphasis of the survey. So maybe let me say briefly what will be the structure of the talk. I want to kind of connect it eventually with some other lectures at the workshop. Namely, so basically I want to first give a survey of my work with Finkelberg and Nakajima and maybe other people about Coulomb branches of 3D gauge theories. And I need to tell you right away, you don't need to know anything, any words from physics. I'm going to actually give mathematical definitions of whatever I'm going to talk about. And second, then I want to switch to discussing similar subject, switch to discussion of 4D gauge theories. And here, well, there will be some constructions in the results, but also there will be in the end what I want to try to get to in the end. I want to get to an open problem, and so I'll say in the end what the open problem is. So an open problem will be about constructing something, and here I want to connect to actually lectures of both Ettingov and Nekrasov. So some kind of, so here you can view everything I'm going to talk about as some kind of very mathematical. You can view it as a very bizarre way in some to construct geometrically a lot of different integrable systems. And so here, when we get to this open problem, so this will be about possible way to construct, let's say, a lot of quotation marks, integrable system of Hitchin type. But that will be something which is not done. But before I get to that, I hope that I will have time to get to that. By the way, I have a question. Do you have 60 minutes or hello?
Yes, you have 60 minutes.
Okay. All right. So let me start. So we start with some very elementary mathematical data. And maybe we'll start with some group G, which, so again, the motivation sort of comes from physics, but in physics, people work with somewhat analytic objects, for example, compact Lie groups and so on. So I want to be completely algebraic. So I'm going to start with G, which will be a complex reductive, maybe connected algebraic group. And I start with something which was historical reason I denote by capital N, which is just a fine dimensional representation of G. And then so the physics tells us to this data, you can attach some kind of structure, and the structure you can attach to it, which is relevant for me at the moment, is something which is called 3D, three-dimensional, n equal 4. Well, that's a different n. Let me write it like this: n equal 4. This n is the amount of supersymmetry, gauge quantum, let's say, gauge theory. And whatever this thing is, well, we as mathematicians don't really know what these words mean, but we can only study some mathematical objects which we believe can be attached to the structure. And so the mathematical object which maybe is possible to define is something which is called the modular space of vector of this theory, which is by itself a very complicated object, so we don't really know how to describe it, but it has some special pieces which apparently do have mathematical definition. And so, so to this we attach to such data, we attach something which is called Higgs and Coulomb branches of the modular space of vector. Now already, so now I want to sort of forget about words from physics. So what kind of objects should those be? Now theses tell us the following, which is kind of not completely precise. So physics tells us this. So I'll denote this by m sub h and m sub c. And so what these things are supposed to be, they're supposed to be hyperkähler. Well, let me again put in quotation marks. Hyperkähler manifolds. Maybe with some additional structure. And I'll talk actually about what additional structure, what kind of additional structure you might want to construct there. So now already here, I want to say that why they put hyperkähler manifolds in quotation marks is that because typically these things are going to be singular. Often singular, and so since it's not completely clear what we should call singular hyperkähler manifold, so therefore mathematically it's this hyperkähler structure is something that I'm not going to really talk about, but I'm going to kind of fix some particular complex structure there. And so so if one fixes a complex structure, then it turns out that one can actually make things algebraic. So kind of slightly different point of view. In fact, they can be defined, again, choosing particular complex structure. Both of these can be defined as affine algebraic varieties. As I said, possibly singular, which are in fact Poisson varieties, so they have Poisson structure, and generically symplectic. So it means that this Poisson structure, in fact, on the smooth locus of this variety, it comes from symplectic structure. I'll give examples in a moment. And so the question is, so question number one for us, and I haven't yet gotten to integrable systems, but there will be integrable systems very soon. Question one, so what is their mathematical definition? So somehow some kind of physics tells us that such objects should exist. And what are they mathematically? And so let me stress that we start with some very simple mathematical data, just the group and the representation. And so now for M Higgs, there is a very simple definition. Well, especially if you don't bother about some details, namely, it's the following thing. So what we do is we take the cotangent bundle to our representation, which is just nothing else but just this representation plus its dual. I should say that by actually secretly from, if you look at this physics definition, that everything should only depend on n plus n star. So for in particular, this, if you replace n by n star, you get the same answer. And this will be apparent for the Higgs branch, but much less apparent for the Coulomb branch. And then what? So if you take this thing, well, okay, let me write the formula, and then so then I take the used to denote it with 3 bars, the Hamiltonian reduction of this by G. So what does it mean? So this T star n, this is just, well, it's a vector space, but it's a symplectic vector space endowed with a symplectic or Hamiltonian action of G. So it has a moment map, which goes to the dual space of Lie algebra. And so M Higgs is mu inverse of 0 quotient by G. Now, of course, because this is usually going to be Navier reaction of G, you have to be careful about what you mean by taking quotient. But here, I want this to be in a final sporadic variety, so I'm going to take the most naive notion of quotient possible, namely, so this is a final variety. So this thing is a spec of the following thing. I take this pre-image of 0 under the moment map, take C of that means an algebraic function, so that then take G invariant function. So this is an example. Well, this is the definition, if you want, of this Higgs branch. And a lot of, so this is some class of groups and representations which are called, where you get something which might be familiar to some people for other reasons, namely, let me say it here. So for example, all Nakajima Weaver varieties are special examples of this construction. Namely, those correspond to what's called quiver gauge theories. And this is the following thing. So suppose that, let's take Q, which is a graph. And let me actually choose an orientation. In fact, at the end of the day, nothing will depend on the orientation, but let me choose an orientation of the graph. And so, well, okay, so we have some kind of graph here with orientation. And then what I want to do, I want to attach some vectors. So to every vertex, I, which is a vertex, I want to attach 2 vector spaces. Find everything find dimensional vi wi. This is just vector spaces. And then I did take the following thing. I take the group G to be the product of GL vi. And I take the representation N to be the following. It's a product over all I. First of all, let me say product over all edges. I goes to J, form from Vi to Vj times product over all I formed from Vi to W. Now, if you take, well, that's a kind of if you just think about groups and representations, this looks like a very not the first example you would think about, but this is a word. This is what sort of quivers give you, and if you run this Hamiltonian reduction construction, this definition of the Higgs branch, in this case, you get, by definition, you get what's called Nakajima covariety. So Nakajima covariety, so MH in this case is called Nakajima covariety by definition. And of course, Nakajima studied those in great detail. He related them to representations of Kazmudi algebras and so on, which is not something I'm going to do because I don't have time. But and maybe examples include things like for example, if you take C2 mod gamma, where gamma inside SL2 C is a finite subgroup, then these things are of this type. And other examples, another maybe type of examples is that if you take, suppose that you take the Lie algebra SLN, or complex numbers, inside here take N, which is nilpotent cone. And this nilpotent cone is a disjoint union of nilpotent orbits, what we call O lambda, and lambda numbered by some kind of partitions in this case. So this is just they're numbered by partitions of the number n. And then for every lambda and mu such that O mu lies in the closure of lambda, there's a notion of transversal slice, which is called Slodoway slice. So I'll call it S lambda mu. This is Slodoway. There's some particular choice of a transversal slice to O mu inside the closure of O lambda. And this is also in a Nakajima covariety. And there are many more examples. I mean, it doesn't have to be. I don't have to be in the context of the Nakajima covarieties, but just what I want to say that a lot of known symplectic varieties arise in this way. Now, okay, so this is the Higgs branch, and now question: what do we know about the Higgs? So question 2 is, what do we know about MC? And so let me, so MC is more difficult to define, and I want to, so, the main point of my short part is to explain how it's, how to define it, and then I want to go into some generalizations. But before I tell you how to define it, let me list some properties that this definition will have. And then I'll tell you how to invent a definition which satisfies those properties. Okay. Any questions before I proceed? So, right, properties of the definition to come. So property number 1 is what I already told you before, but I'll say it a little bit more precisely, that MC is an affine normal Poisson generically symplectic. Well, let me just, instead of writing generically symplectic, let me write kind of in quotation marks symplectic. So it means that it's kind of as symplectic as possible. So for example, if it's smooth, then I want it to be really symplectic. And at least, for example, I want to be the whole smooth locus to be symplectic. And actually it's of dimension. Dimension turns out to be independent of the representation twice rank G. Second, and this is already is going to be related to something I mentioned at the very beginning, MC is going to be endowed with a canonical integrable system, and the integrable system, so there will be some map, let me call it phi, and the base of this integrable system will be will always be the same. So it will be, well, let me write it like this. So here I choose T inside G. This is a maximal torus. This T is its Lie algebra, and W is the Wall group. And so there will be some map like this, which is a completely integrable system. So it means that the fibers of this map are Lagrangian subvarieties. In fact, generic fiber will be, well, I mean, usually when you have an integrable system, classical integral system, you want generic of this fiber, you want to be torus in some sense. Now, the word torus in mathematics means a lot of different things. So if you're doing a real manifolds, then torus is a circle to some power. If you're doing affine algebraic geometry, then a torus means that it will be just C star to the power, in this case, rank of G. And later on, when I get, if I have enough time, when I get to this open problem part that I mentioned, then it will become more interesting, because I promised to say something about integrable systems of Hitchin type, and there will be conjectural, there was some similar construction where the fibers will be some abelian, generic fibers will be abelian varieties. Okay, so that's structure number 2. Structure number 3 is that MC will come with a special, with a canonical C star action. With respect to which, so it means that its algebra of functions has a canonical grading, with respect to which the Poisson structure has degree -2. In other words, if you think about symplectic varieties, then it means that we have a C star action, sort of dialects the symplectic form with weight 2. 4 is that everything here will actually come with a canonical quantization. Canonical of these structures. So it means that so if we let AC be the algebra of functions on this thing, which is supposed to be Poisson algebra, and we have an integral system, so it's endowed with some special, sufficiently large Poisson commutative subalgebra, then there is a deformation of this depending on parameter H bar, which is already, well, non-commutative deformation, inducing the corresponding Poisson structure deformation, and everything here deforms. For example, integrable system deforms. So that's structure number 4, and maybe last structure I'm going to mention before we talk about it. So I want to mention a few examples, and then I want to talk a little bit about the construction. There's something which physics call flavor symmetry. Namely, suppose that there is another reductive group. So assume that we have some group G sub F. F stands, the letter F stands for the word flavor. This is what physics call flavor symmetry, which sits inside the automorphism group of our representation. So suppose that we have something that our representation is not irreducible. For example, we have something bigger acting on this representation. Well, actually, sometimes even for reducible representations, you can have this because somehow for reducible representation you have just C star, which dilates everything, which sits inside the automorphism group. Then all of the above has a, well, has means canonically given. Has a deformation over the following base. So we take T sub F. So T sub F means, again, the Lie algebra of the maximal torus for this flavor group. Modulo WF, so which is the Dual group over of the flavor group. You can also think about this as G sub F modulo adjoint action. So that's kind of the structure we want to, we're after. Let me give you one. So I should say that, again, I want to stress what I have already stressed, that we start with an extremely simple mathematical data, like something which people in the 19th century were working with. So just have a kind of reductive group, for example, GLN or something like this, and we find the most representation. For example, this representation can be zero. That's a pretty interesting case already. And then we're going to sort of attach this kind of relatively rich mathematical structure to that. And now I should say that when we take a sufficiently general group G and kind of sufficiently general representation, then it doesn't make sense to ask what we get, in the sense that we get some varieties which sort of have never appeared before. So only some very rare cases we might present an answer to what these Coulomb branches are in explicit terms, because explicit terms by definition mathematics means that you're kind of describing it in terms of something that existed before. And so in those cases, these are not varieties which have ever appeared before. But in some cases, they are familiar varieties. So let me give an example. So there are very few examples which work, where I can say something for arbitrary group. For example, you can do the following. Suppose that take any G and take this M to be the Lie algebra, so this adjoint representation. Because G is reductive, adjoint representation is the same as coadjoint representation. In this case, we can actually describe this thing explicitly. And so, this is a very simple answer, which I'm going to present, but it's the only case when we have a really simple answer. Namely, in this case, this MC is going to be the following thing. So we take this maximal torus, then we take the dual torus. So for every torus, there's a canonical dual torus, so such that its character lattice is the core character lattice of the original torus. Then I'm going to write the following. So in this whole business, I always have a huge notational problem, because I want to take cotangent bundle to this torus. And so if you denote torus by T, then when you write cotangent bundle, it looks awkward. But so maybe you can say that you should denote, I mean, the standard notation for a maximal torus of reductive group is H, but H is not good either, because very soon we're going to consider some cohomology everywhere. And so H in notation H is going to interfere with cohomology. And I think this problem is unresolvable. So let me just write it like this. But here, the meaning of the two T's is different. So one T stands for the torus, the other T stands for the cotangent bundle. And then, on the torus, we have the action of the Weil group. So we have the action of the Weil group on the whole cotangent bundle. So we just take the quotient by double. And note that this cotangent bundle to the torus, it's nothing else but this torus times the dual space to its Lie algebra. And the dual torus is defined in such a way that the dual space to its Lie algebra is more or less by definition the Lie algebra of our region. So this thing looks like this. So before we take the quotient to the by the Weil group, this thing has a canonical map to T. And then when we mod out by the Weil group, this obviously has a map to T mod W. So that's our integral system. So that's a very, well, that's actually, this is a very important case, but that's kind of a really simple case. And that's the only case when we can, where we can sort of describe things in very simple terms and kind of uniformly independently of G. Then there will be some examples which I'm going to present a little later for some specific choices of G and M. There will be some interesting answers. Okay, any questions so far? Okay, so if there are no questions, let me maybe let me give you another uniform example. But that example is going to be it looks like it should be simpler than this, but in fact it's more complicated, at least in terms of the answer. Namely, again, take any G and take this representation N to be 0. In the physics language, this is called pure gauge theory. So in fact, this representation N, this is really closely related to the matter in this gauge theory, and when it's 0, this is what's called pure gauge theory. Then what is the answer here? The answer here is something, let me describe it, something which is called the universal centralizer. So I'm going to describe it as a variety. By the way, it's not something in the previous example, something which I forgot to say it, but it's kind of clear that this thing it's clear that this thing is more or less symplectic. So the cotangent bound to torus is symplectic on the nose because cotangent bound to everything is symplectic, and then we just mod out by some finite group. In fact, when we mod out by this finite group, we get something singular, but it's clear that this action of this W, it preserves the symplectic structure. So when we mod out by W, at least we get a Poisson variety, and it's clear that generically it's going to be symplectic. So in this example, I'm going to present the variety and this integrable system, but the symplectic, in fact, in this case, the variety will be smooth. So in fact, it will be just a symplectic variety, but the symplectic structure will not be apparent from the construction I'm going to present. So to have a symplectic structure, to define a symplectic structure, you need a different presentation of it, different construction of it, which I won't talk about. So I'm not going to. So I'm going to try to tell you what the variety is, but I'm not going to tell you how to define a symplectic structure. But the claim is that it does carry canonical symplectic structure. Namely, this thing is the following. It's kind of the modular space of the following data. So you can see the pairs. X in G. Let me put G star, but it doesn't matter. I mean, of course, G and G star are isomorphic, but it's kind of more canonical to write it in G star. And here I put reg. Reg means it's a regular element. So regular element, for example, if you think about the group GLM, then G or G star, this is just n by n matrices, and regular element, it means it's a regular matrix. It means that that's characteristic polynomial is equal to its minimal polynomial. Or a general definition of regular means that its centralizer in the group is of minimal possible dimension, which is equal to the rank. And so we take pair X, which is a regular element, and G in G such that these things commute. And then we went out by conjugation. So, well, as usual, when you can see the quotient, you have to sort of work a little bit to make sense of this, but in this case, it's actually not a big problem. So, so this is a variety. So this is going to be our variety. So what is our map pi? In this case, our map pi in this case is going to be the following. It's sort of only, well, kind of, well, it goes to, oh, oops, sorry, there's something sorry, there's something I'm doing wrong here. So here I need to, I forgot I have to do it for the dual group. So here, maybe let me write it here. So when I start with this group G, there's another group you can attach to G, and it's called the group G check, and this is the Langlands dual group. And it's characterized by the condition that, well, one way to describe it is to say that a reductive group corresponds to some root datum. And so G check has root datum dual to that of G. So I forgot that here should do it this way. And so this goes to, so we should construct, we're going to construct a map to G check star reg mod G check, which is the same, actually, again, it's, if you look at the definitions, canonically the same as our original T mod W. And so this pi just sends this pair XG to X. So it only remembers the conjugacy class of X. So the modular space of regular conjugacy classes is the same as the modular space of all conjugacy classes. So it's kind of, if you think about the Lie algebra, the group GLN and Lie algebra, which is just matrices, then we're just saying that this T mod W, this just remembers spectrum of a matrix, and we're saying that for every, basically the statement is that for every choice of spectrum, for every choice of eigenvalues, there's a unique conjugacy class of regular matrices with these eigenvalues. So that's, and then, well, let me maybe leave this as an exercise, but it's not a completely trivial exercise. Define a canonical symplectic structure. Let's call this thing capital Z, because Z stands for the centralizer, so this is called the universal centralizer. Define canonical symplectic structure on Z, so that pi is an integral system. So secretly, this integral system is closely related to what's called open Toda integrable system, but I'm not going to comment on that now. Okay, so okay, so I have a question. When exactly am I supposed to finish? So, I mean, I know it's 60 minutes, but I think I started late, or am I supposed to finish exactly at 4 o'clock, or is it
Oh, Sash, it's a bit flexible. So it would be nice.
Okay,
if-
well, I don't want to go like terribly over time, but let me know what is the expectation.
The expectation is 4 o'clock. And if
Okay.
you go over like by 5 minutes, I think
Okay, fine.
it'll be okay.
Okay, so let me give you, I'm not going to probably give you the details of the construction. So now let me talk about construction. I'm not going to give you details, so let me actually give you the actual construction for the n equal to 0 case. And then I'm going to say that there is a relatively easy way to generalize this to arbitrary n. Maybe I'll just mention the brief idea, but so construction. So let's take n equals 0. Then construction is the following. Well, after all, we want to construct some affine algebraic variety. So when we want to construct some affine algebraic variety, it basically means that we want to construct some algebra of functions on this affine algebraic variety. So we're after some algebra. Now the idea is that so in this case, I wanted to call this algebra AC. This algebra AC is going to be defined as homology of something. And I'll talk about what this something is. Now, already here, you may ask a question. So usually homology doesn't have an algebra structure, and cohomology has an algebra structure. But sometimes homology has an algebra structure. For example, if you take something like homology of a Lie group, then multiplication on a Lie group induces multiplication in homology. And this is kind of what's going to happen here. But to say these things precisely, we need to introduce something which is called the affine Grassmannian of the group G. Namely, let's introduce the following notation. Let's introduce the field K, which is just the field of Laurent power series in the variable T. And inside we have a subring O, which is the ring of Taylor series. And then we define the affine Grassmannian of G, which is some kind of infinite dimensional object, but not terribly infinite dimensional, which is just the quotient of G of K by G of O. Well, okay, the way it is written now, it's only written as a set, but we want to define some kind of object, an algebraic geometry. To define some algebraic geometry, well, the correct way to think about infinite dimensional objects in algebraic geometry is to define its function of points. To say what it means to map some affine scheme into that. I'm not going to do this, but somehow the claim is that this thing is what's called an int scheme. And in fact, it's int projective. So it's equal to direct limit of projective algebraic varieties. I'm actually cheating slightly here. So this is literally group G semi-simple. If G is semi-simple, is reductive but not semi-simple, then things are slightly more complicated. But again, let me ignore that. So in fact, for every lambda, which is a dominant weight of G, we can define some, there's a G of O orbits at some, actually, well, let me say it like this, sorry, let me say it slightly differently. So this affine Grassmannian, just first as a set, it's a union, disjoint union over lambda, which is a dominant co-weight of things of the which I'll call lambda G. And so there's a G of O orbit. So if you try to classify G of O orbits on this affine Grassmannian, then the one corresponds to dominant co-weights, and then in appropriate topology, the closure of every such thing, this is projective. Right. And then you can now take the following thing. We can take, in this case, this AC is going to be, well, I want to take the homology of the Finkelberg, but in fact, I want to take the equivariant vector for homology of the Finkelberg. And so know that I can formally write it as homology. Well, if I use notations with algebraic stacks, then I can write it as a homology of the double quotient. And if I write it like this, then it's not inconceivable that this homology is going to have an algebra structure, because I said that if you take just a group, then homology of a group is going to have an algebra structure, and the algebra structure is induced by the multiplication of the group. And the same is true that if you take a group and a subgroup, if you consider homology of this double quotient, which you can define as homology of one side of the quotient equivariant with respect to the action of the other side, then the same multiplication in the group is going to induce algebra structure here. Now, what is not completely obvious, but true in general, there's no reason to think about to expect this homology is commutative. But lemma says that in this case, AC is commutative. So that's kind of the definition for n equals 0 case for the pure gauge theory. And for general n, one can define a similar space, which we call RGN. This is some space which maps to the Finkelberg. Well, in fact, I can even tell you what the space is. So namely, it's so this RGN consists of pairs G in G of K mod G of O, and let's say N in N of O, such that G of N again lies in N of O. This makes sense. I can give a more geometric description of it, but unfortunately I don't have time. But the point is that this, at least this formula makes sense, because obviously this condition G of N lies in the N of O. Sorry, let me actually write G inverse of N as O. So if I write it like this, then the point is that if I multiply G by G of O on the left, then G inverse is multiplied by G of O on the, sorry, if I multiply G by G of O on the right, then G inverse is multiplied on the left. And then this condition that G inverse of N is an N of O doesn't change. So this is some space I can forget about this N, and then this kind of naturally projects the Finkelberg. Well, and then this AC in this case is, unfortunately, I need one more ingredient, which I'm going to hide the definition under the rug, and this is, I need to call something which is called Braverman homology of the space, equivariant with respect to G of O. The space is slightly infinite dimensional, so you have to work a little bit by what you mean with what you mean by Braverman homology, but it's not difficult, and this is done. In our papers of this RGN, and this is and again the same type of convolution, sort of induced by multiplication of the group, will also make sense here. So this thing will be commutative function. Now I should say that this definition, if you sort of read the physics literature, then this definition is not as crazy as they think, because in physics, physicists tell you that functions on this Coulomb branch are given by some kind of monopole operators. And if you sort of try to understand what physicists mean by monopole operators, then it's kind of not very difficult to convince yourself that these monopole operators are precisely homology classes of such a space. So this is Borel-Moore homology again. If you don't know what this, then just I'll say that it is some version of homology, which is for compact spaces it's the same as ordinary homology, but so for non-compact spaces it's something slightly different. And so that's kind of the definition. And so the idea is that non-commutative deformation comes from the following thing. So let me explain the non-commutative deformation. It's the following thing. So we should consider the same homology of the same space. But now we should consider its equivalent respect to a little bit more than this. There's another C star acting on the whole thing, which is called loop rotation. So this C star is the what's called loop rotation. So let me do it in the case when n is equal to 0. So when n was equal to 0, then this RGN was just the affine Grassmannian G of k mod G of O. And so C star just rotates the variable t. And so, well, I don't have time to explain the details, but the idea is that when we do this, so I said that there was a lemma that this convolution algebra, that this homology algebra is commutative. So we actually have to prove this lemma somehow, but it turns out that the proof doesn't work if we introduce this additional covariance with respect to loop rotation. And so when we start to loop rotation, then everything becomes a module over the equivalent homology of a point with respect to C star, which is the algebra of polynomials in one variable. So this is algebra over equivalent homology of a point with respect to C star, which is algebra of polynomials in one variable, which I want to call H bar. And so, and this H bar turns out to be the Planck constant in the sense that it defines the non-commutative deformation. And the last thing I'm going to say about the general construction is that this integrable system is the following thing. So if I take this, well, again, whenever I take this, well, kind of homology, Borel-Moore homology, cohomology, doesn't matter, of anything. So this contains inside, well, there's some unit, it's a module over equivalent homology of a point, because there's some unit homology class here, then, and this is an algebra. In fact, it's an algebra over, so this thing contains equivalent homology of a point with respect to G of O. And G of O, if you think about it, homotopy, well, when it started as some kind of equivalent homology, cohomology with respect to some group, then the answer only depends on the homotopy class of it. And then homotopically, this G is this G of O is the same as G. That's easy to see. So G of O is kind of infinite dimensional, but the whole infinite dimensional part of it is something contractible. So homotopically, it's the same as G. And so this thing is the same as equivalent homology of point with respect to G, and that thing is the same as the algebra of functions on what we call T mod W. That's so. Therefore, this algebra contains this C of T mod W, and from the definition of my non-commutative deformation, it's kind of and so I told you how to define non-commutative deformation. This non-commutative deformation defines, sorry, this non-commutative deformation defines a Poisson structure, and it's an easy exercise from what I said that these elements, this function on T mod W, the Poisson commute. Okay, so I'm close to the finish. So now let me spend just a few minutes talking about some generalization of this. Any questions before that? Okay, so
I believe you can have a few minutes.
okay, generalization to 4D gauge theories. Let me say 4D and equal to supersymmetric gauge theories. Now, the idea is that, so again, if we believe in some words coming from physics, then we said that somehow when we start with a group and a representation, we can associate some quantum gauge theory to that thing, or some three-dimensional quantum gauge theory. And so, by the way, here, well, if it's three-dimensional, we can sort of put it on a free manifold. And in the whole previous discussion, this free manifold was just R3. And so, and now now the claim is that the same data actually defines some four-dimensional gauge theory. Now, if you actually look at physics literature, then physicists will tell you that in order for what they call physical theory to exist, there's some very strong condition on this M has to be satisfied. So, for example, if G is a torus, only the zero representation will work. But actually, I'm going to ignore that. So somehow the point is that if you want to define some analytic objects which require some conversions, something like hypercalometric or things like this, then you really need this physical theory to exist. If you wanted this if you only care about algebra, then essentially you don't need this physical theory to exist. For example, you can make things work. You're supposed to be able to make things work for every G and M, for every group and every representation. And so, but formally speaking, we work on a form manifold, which is R3 cross S1, some kind of four-dimensional cylinder. And in this case, this MC is again supposed to be hyperkähler manifold. Well, again, let me put in quotation marks because it's sometimes singular. Also, it will be truly hyperkähler only for some nice representations M, but for what I'm going to say, it won't matter. But it will be hyperkähler manifold of a very different type than before. Because before, well, in this 3D story, I only talked about this thing in one complex structure, but there was some reason for that. Namely, somehow this is some boring hyperkähler manifolds in the sense that they're going to look the same in all complex structures. And these hyperkähler manifolds, which correspond to 4D gauge theories, they will look differently in different complex structures. So for example, generically, for generic complex structure, they still will correspond to some affine algebraic, right? But in some special complex structure, they will not be affine anymore, but they'll be projective over affine. And in fact, they will still carry an integrable system. And the integrable system, so in the generic complex structure, what will be the base of the integrable system? Generic complex structure. This thing will live over, this time, multiplicative version of what we had before. It will live over the actual group torus mod W. And and the special complex structure, this will, the base of the integral system will be the same. But the difference from what we had before is that now in the special complex structure, this is a projective. This is supposed to be projective morphism. And so here, well, let me put this generic here. Let me put this as P for special. So, and so I'll call this map pi generic, and this map pi special. And so generic fiber of pi generic is still isomorphic to C star to the power rank of G. And generic fiber of pi special is supposed to be isomorphic to an abelian variety. And moreover, this abelian variety should vary when we vary the point in the base. You know, see, when we write C star, see the difference between a fine algebraic torus and kind of algebraic torus in the sense of abelian varieties is that all affine algebraic tori are isomorphic. And of course, not all abelian varieties are isomorphic. And so the question is how to define these things now. Now, in the generic complex structure, there's an answer. So for MC generic, we do exactly the same as before, but we replace homology by K-theory. This is spec of K-theory geovoid covariant of the same space RGN. And then basically everything we can do, we do for homology makes sense for K-theory. If we introduce this loop rotation that defines an ultimate deformation. And so this is just the kind of variant. So then we can compute examples, but at least the general definition is the same. For MC special, at the moment, there is no definition. And that was the open problem I want to talk about. So I want to say just 2 words what I want this definition to be, and then I will be done. At the moment, no definition. Although physicists, for example, Nikita computed a lot of examples. For example, Nikita and Gaston computed
Sasha,
the answer for all the Coulomb gauge theories.
I believe we have to stop.
Okay, let me just say one last sentence. So what I want to say is that this thing is supposed to be projective over affine. So therefore, well, before we define just algebra functions, and here this thing does have the algebra function, but this thing is supposed to be is supposed to have projective homogeneous coordinate ring, because the fibers are supposed to come with the canonical projective embedding. And then sort of very vague conjecture, and this is what I want to say is an open problem, that homogeneous coordinate ring should be defined in the same way as in 3D, but replacing G by the corresponding affine Kac-Moody group. So basically the slogan is that I want to think about 4D gauge theory as something like 3D gauge theory for the loop. And so I think it would be extremely interesting to make this precise. I can actually make this a little bit more precise than I said here, but I don't have time for that. But that's kind of the challenge in this theory. And so then last sentence I'm going to say is that this will be a way to define a lot of integrable systems of Hitch and type, because this MC in this special complex structure, the corresponding integrable system, they are kind of true integrable system with generic fibers being abelian varieties, and many examples that should be related to some kind of Hitch system. Okay, thank you very much. And sorry for going over time, and sorry again for
let's thank the speaker. We have 1 minute for short questions. Are there any questions? Sasha, the abelian varieties that arise as fibers, are they related to Jacobians of curves?
Well, in general, there should be no reason for them to be related to Jacobians, but somehow sometimes, yeah. For example, if you take this pure gauge theory, then you know, well, many examples, you know what answer you want to get. For example, if you make pure gauge theory, then you're supposed to get what's called a fine Toda integrable system. And for example, in type A, the corresponding abelian varieties are exactly Jacobians of some curves, which are in this case called Zyberg-Witten curves. So this is the actually Zyberg, well, Zyberg and Witten, maybe Tanaka and Witten tell you that any 4D equal to gauge theory should be sort of controlled by some integrable system. And I think one of the purposes of Nikita's lectures are to describe these integrable systems. So this is exactly this integrable system. So the thing I'm after is kind of general definition of this integrable system. And what I presented before is that in some related but simpler setups, we know kind of a very general definition. And I believe there should be a very general definition in this case too. But for this, we have to work with spaces which are more infinite dimensional than before, so to say. So therefore, I never tried to sort of push this rule carefully. I can again say what I want more precisely than I just had time to do it here. But in principle, as far as I know, in this generality, there's no definition of this thing at the moment. But I think there should be. So there should be some kind of integral system of this type for any G and any representation.
I see one more question.
Okay, so I heard that before some physicists define the Coulomb branch as character varieties. So what's the relationship between this definition and that one?
Well, I mean, it will be something like character varieties in some very special case. So for some, it will be the case for quiver gauge theories for some very special quiver.
Okay, thank you.
But in general, they're not going to have anything to do with quiver varieties. And in general, the point is that they're not going to have to do with anything, in the sense that these are really genuinely new spaces which have never appeared before in any incarnation. So therefore, it doesn't make sense to ask how to describe them because you have no language to describe them. So those are kind of really new things. But in some special cases, for example, if you take quiver gauge theories of, say, finite or affine type, you have a very explicit answer, and so in some other cases. So, but somehow the thing I want to do at the moment, in terms of this open problem, is to actually have a general definition in this special complex structure. And
okay,
this is not
let's thank the speaker once again.